probability and statistics, estimating population parameters. This is a small part of what is called statistical inference, making conclusions, drawing conclusions using statistics. In this case, we're looking at a population, and because the population might be too large, so it might be impossible to do a study on the full population for various reasons, time, costs, etc., we take samples from the population. So we'll take a sample, randomly chosen, and we'll explore its data and we'll analyze its data. From there, we'll make inferences and work out probabilities about the actual population. It's one of the most important functions in statistics. So it's about populations and sampled. The population includes all members of the group about which we're making inferences. So if we're making a study of primary school boys in the country, then the population consists of all the primary school boys in the country. A sample is a subset of people, items, events from the larger population that you collect and analyze to make inferences. And of course you have to choose it randomly, and that's fairly complex and takes quite a bit of qualification and experience to do that, because when you do a study with research and conclusions, they're very critical eyes looking at it to see whether in fact they are relevant and whether they are significant. To represent the population well, a sample should be randomly collected and adequately large, and perhaps a number of samples. For example, going back to that primary school boys, Travonia Primary, chosen randomly, could be a sample of the population of all primary school boys in the country. Now, obviously, we won't be able to do one alone, because if you think of there's a huge range of different schools in the country, from private to public to very poor schools with few resources to wealthy schools with plenty of resources, and that's all going to affect your inferences made. So you take the population, from it you draw a sample, you observe the data, and then make inferences back about the population. There are two types of estimates. The point estimate, which isn't terribly useful, it's a single numerical value calculated from a sample. This is used to give an indication or an approximation of the value of an unknown population parameter. So we might, for example, take a sample, find its mean, and then say that is the mean of the population. You need to be careful with standard deviations, because standard deviations change considerably depending on the size of the sample. And the bigger the sample, the more the standard deviations are going to change. So formally you have to allow for that. An example, a study on the body mass index of all male students, university students between the ages of 19 and 25 in the country. Notice fairly specific. This university has chosen at random. The mean BMI of all students meeting those criteria is used to approximate the mean BMI of all students in the country. And a number of other point estimates, some of which involve proportions. For example, estimated overall HIV prevalent rate is 11%. And that one would do from taking samples and working out that the sample prevalence rate is 11%. It's a bit dangerous doing a point estimate. It's actually far better to do an interval estimate. That consists of a range of values rather than the single value within which the actual population parameter would be found. So it then takes into account that sample results may vary, and it gives an indication of how much variation can be expected. And we're going to call the interval estimate the confidence interval. What we're going to say is we are confident that the population mean falls between these two values. Well, that the probability of it falling between these two values, we'll have to give our confidence in terms of probability. So we might say the probability that it falls between these two values is 90%. In the previous example, the sample universities are used to determine the interval in which the BMI is likely to lie. So we might imply and say, well, the mean BMI of male university students between those ages, the probability that it falls between 19 and 27 is 95%. Further example of interval estimates. Here's one here, a study done in 2003 on the number of people with HIV, infected with HIV or AIDS in the United States. This would have been obtained by taking a sample because you could not test every person in the United States. And these are actually proportions. So let's investigate the distribution of the sample mean. Why I'm doing that is that often we'll take samples to try to estimate what the mean of the population is. Often we'll take samples and say, well, the average weight of the people in the population is 67.3 kilograms. How did we get that? By using samples. But it's safer to say the average weight would lie between these values at 95% confidence level. So a box contains a large number of cards. Each card has one of the numbers 147 written on it. A sample of 3 cards is taken from the box and the mean of the 3 cards is calculated. Now note that to get a mean of 1, we could only choose 1, 1, 1, and there's only one way to do it. But if you wanted to get a mean of 4, which is what this is, we could choose 147. If we want a mean of, well, that's why this one here, we're looking for a mean of 4. So we do 147, 417, 741, etc. And 117 could be obtained in those different ways. So for a sample for the mean of 3, we could choose in those 3 ways. And there might be other ways. Now, probability needs to take that into account. We might say these are the same thing, but in fact, if these are the same thing, why is it that there's more chance of getting this than 111? Oh, because there are 3 ways to get it. So these need to be taken into account in probability. So the mean of that sample is 3. Write down all possible samples of the 3 cards. You must include the different ways of obtaining the 3 cards. Alright, so there are all the possibilities. And there are all the possibilities with the permutations. Now, calculate the mean of each sample. Well, you should have 7 different means. That's why the 1 and 2 4s and the 2 1s and a 7 are grouped, and the 2 4s and a 7 and the 2 7s and a 1 are grouped because they have the same mean. There we are, there. Now complete the frequency table. There's the sample means. Frequencies. So there are 7 with a mean of 4. Those 6 and that one. And that's how we obtain those various frequencies. Remember now that we are finding these sample means with a view to estimating the mean of all the cards in the box of the population by just using these samples. Right, draw a bar chart of these means. There it is there. And you'll notice that they actually do form a shape. It's the normal distribution. So the sample means do form a normal distribution. Note the range of the sample means, from 111 up to 777 and anything in between. So now if we had to try to use that to estimate the population mean, we'd have a bit of a problem. The population mean is 4, but look at all the others. So in using the sample mean to approximate the population mean, those are pretty accurate, but those other ones, the yellow ones, are questionable. They're pretty far out. But they are still samples which came out. So as the sample size increases, though, if we use more and more cards, we'll find the range of the means will increase. The range of sample means will increase. The representation more closely represents the normal distribution. Now remember, the range of the means is the frequency. So the frequencies definitely will increase. I mean, there's no ways about that. The representation will more closely resemble the normal distribution. So each value of the sample mean can be a point estimate, but not all of them would be good approximations of the true sample mean. So once again, we're saying a point estimate is not that good. We could have chosen that sample and said, oh, therefore all the cards in the box have a mean of 2, which is really out. So we need to look at it a different way. So we look at confidence intervals. In the previous question, there are 7 different values for the sample mean. Taking one of these could give you something far from the actual population mean. So it's better to give a range of values of which there is a reasonable probability that the true population parameter falls. So if we said, well, it's the population parameter, the population mean falls between 3 and 5, that would be better. But in the same way, there too, when we say it falls between 3 and 5, we must give the probability that it falls between those. We can't just make some vague statement. Confidence interval indicates the reliability of the estimate, usually as a probability, and that's what we mean by the confidence interval. So I would say that there is a 95% probability that the population mean, the mean of all the cards in the box, falls between 3 and 5, and then that would be stating it correctly. Sample means of any size n from a more normal distribution also form a normal distribution. But notice now that the normal distribution of the sample means has a variance of the sample divided by the number of elements in the sample. So, standard normal distribution has a mean of 0 and a standard deviation of 1, and the area under the curve is 1. If you're not sure of this, you need to look at the standard deviation, at the normal distribution videos. There are 4 of them. There's a set of 4 of them in this video group. So now, the Z table gives us the area under the normal distribution curve between the mean and the Z score. So for example, if I look at the z-score of 1.3, which is a standard deviation of 1.3, so it's the standard normal deviation, which has a mean of 0 and a normal distribution. The z-score of 1.3, which means 1.3 standard deviations, has a certain probability, because the probability is the area under the curve. So the probability of something falling between 0 and 1.3 is the area under this curve, and that'll be the z-score. You look up 1.3 on the z table. So, between 0 and 1.3, remember the z-scores are always between 0 and that, and if we have a negative side to it, we have to reflect it to the positive to make our conclusions. So it's 0.4032. So it's a 0.4032 probability that a score lies between 0 and 1.3 on the standard normal distribution. Now that's on the right of 0.8. So now we have to be careful, because if we talk z-scores, it talks between 0 and 0.8. But we do know that the area under the standard normal distribution curve is 1. Therefore the area under a half is 0.5. So we know this area is 0.5. We know the z-score, the standard deviation of this normal distribution, is 0.8. So we can find the probability, which is that area associated with 0.8. And therefore the 0.5 of this whole area and the actual z-score, the probability for this area, could be combined by subtraction to give us the area required. So, probability Z is bigger than 0.8 is 0.5, 50% minus the probability that is between 0 and 8. And there's the z-score for 0.8, which we can subtract, and there it is, 0.2119, 21.19%. Here's another case between two scores. Now we can easily find the area to 2.1, that's the z-score, and we can find the area to negative 1.6 because it relates to the area to 1.6. It's equal to it. So we're going to find z-score 1.6, z-score 2.1. We're not going to say, oh, z-score negative 1.6, so the z-score is negative, because the z-score only works positive, and there are two positive areas we're adding. So, there's the z-score for 1.6, there's the z-score for 2.1. We're going to add them together, and the probability is 92.73% that it lies between those two. Now that's what we're going to do in estimating the population mean. We're going to say, oh, the probability is 95% that it lies between these two values. Now, if we have other normal distributions other than the standard normal distribution, remember the standard normal distribution has a mean of 0 and a standard deviation of 1. So all we have to do is use this magic, but not so magic formula really, to work out z-scores standard deviations away from the mean. So to work out how many standard deviations away from the mean. So we take the score minus the mean of that distribution, divided by the standard deviation. So if the score was 2 standard deviations away from the mean, then that minus the mean will give us 2 standard deviations, divided by the standard deviation will give us 2. So this gives us the z-score for any normal distribution. But in the case of a sample, we must see the standard deviation as the standard deviation of the sample divided by the square root of the number of elements in that sample. Something you just need to know. And that's the population standard deviation and population mean. Right, so to do that, there's our formulae. Large samples, n greater than or equal to 30, approximately follow a normal distribution of that. Large samples. So if we choose just 6, I don't know whether it will. 95% of the variable values lie within 2 standard deviations of the mean. How do we get that? By using the z-score of 2. The z-score of 2 will give you half of that value, being half the area. So therefore the z-score must be half of that, 47.5, to give us this situation. The z-score must be 49.9 to give us the 3 standard deviations. So extending the value of the sample mean to approximately 2 standard deviations will give us a 95% probability that the interval includes the actual population parameter. And why? Because the 95% 2 gives us approximately 47.5. 3 types of cases made up, and we're not going to do all 3. We could have a large sample, or one of any size. We could have a population which may be normally distributed or not, and the statistician has to take this into account. And the variance of the population may or may not be known. Now, this course, we're only going to do the one, and that is, we'll look at the one where it's any size sample, the population is normally distributed, and the variance of the population is known. So, here are the confidence levels. Now, to get those, all we do is look up, find what z-score relates to 45, to 47.5, 49, and 49.5. Then we're looking at half the distribution curves area. So that takes us to the closest values. So that's important now, because that means if we want a 99% confidence level, we need to look, there's 99, we need to look and make sure that we can say that the population, 90%, we're 99% sure that the population will lie between negative 2.576 and 2.576 critical Z value. But of course, we will have to interpret that back to whatever we got from the sample in terms of actual mean and standard deviation, because this is not the sample and we may not be talking about a standard normal distribution. So here we are. Lengths of 10 worms. There they are, length of 10 worms. Given the variance is 2.25. So samples follow that approximately. Notice that is of the population. So it follows normal distribution with those parameters. Sample mean length. Well, we're going to add them and divide by 10. That's how we get 7 centimeters. So we now know the population mean. Now the 95% confidence interval, we're going to look and say, well, 95%, the z-score must be between 1.96 and negative 1.96. Z-score of 1.96 means negative 1.96 and 1.96. Which means now that our formula for the z-score for the sample If we equate it to plus or minus 1.96, it'll actually give you the values of the population mean, because that's what we're trying to find. So we know the population standard deviation, we know the sample mean, we found it, and we know the sample size. So there we are. Remember, that's, where did we get that from? We got that because we're looking for 95% confidence level, which is, of course, the value at 95, 1.96. So we end up with the population mean of 7 plus or minus, because there, when we solve this for mu, the population mean, we get 0.9297. So there it is there. What conclusion have we made? We have said that there is a 95% based on this mean, and knowing that that is the variance of the population of earthworms, that there is a 90% probability that the mean of the population falls somewhere between 7 plus and 7 minus. So 95% probability that the mean of the earthworm length falls between those two values. So now we're going to do 99%, so we're going to do the same thing. We're going to take that, we're going to equate it to the z-score for 99 there, and we're going to solve again for mu. So it's 2.576 for 99%. We're solving again for mu, we know everything else, and that is the, there we are, there is the mu, 7 plus or minus that value there. Which means we are 99% confident based on this sample and the fact that the variance is 2.25 of the population, that the mean of all the earthworms in the garden will lie between those two values. And that's all the research can do, is say the probability is 99% that this is the case. Confidence interval for proportion. So now this is where we're actually estimating proportions now. 15 to 20% are such and such. Proportion of the sample is calculated by finding the ratio of number of people with the particular attribute to the total number of the sample. If we take the sample of n observations and number of successes is x, then the sample proportion is x over n. Well, if the sample's 5 and there are 2 successes, that's 2/5, 40%. That's written as circumflex p. That's a circumflex. There, you've learned a big word like marmalade if you didn't know it. There's the mathematical notation for it. Or just hat p. P hat. P hat, we say. And it's binomial because it's success or failure. And the complement is q hat. And how do we find q hat? Q hat is the difference between p and 1. P is 1 minus q hat, or p hat is 1 minus q hat, or vice versa. Formula for the confidence interval of a proportion is given by that. Now that looks terrible, but in fact, not too bad. That's q for a start, q hat for a start. So we can abbreviate it to that. And this will always be given. So remember, p for proportion, that's the proportion of the sample plus or minus the z-score required for the confidence interval required. Square root of proportion of successes times proportion of failures over number in the sample. So there it is there. And then the confidence interval for proportion is between those two values. So let's have an example, look at an example. A sample of 300 learners established that 30% of them are left-handed. Set up a 98 confidence interval estimate of the population proportion. Well, 30% are left-handed. Now that's almost like the mean we did before. So P hat is 30, so Q hat is 70, 0.3, 0.7. 98% confidence interval, so we will actually now look up the Z-score for 98%. There it is there. P hat 0.3 is the proportion. So therefore, knowing that's the case, we're going to apply a formulae. P hat minus the Z-score, 0.3 times 0.7, success failure, over 300. Because that's the sample size, and same there, and there's our answer, which means that we can say we are 90% sure, 98%, there's a 80% probability that between 23.8 and 36.2% of the population are left-handed. A sample of 200 people interviewed by a fresh fruit company. A total of 80 people in the sample said they only drink 100% pure fresh juice. Found the 95% confidence interval for the proportion of people who drink only pure fresh juice. Well, we have 80 out of 200, so we work that out, and so P hat will be 25%, 0.25. 0.4, where am I getting 25 from? Call myself a mathematician. Sorry, 80 divided by 200, 0.4, P hat. Now it's 95% confidence interval, so we look up 0.95 on the Z table, unless we've memorized it by now. There it is. And we're now going to apply our formula. We know P hat, 0.4. We know the Z score. We know P hat. We know 1 minus P hat or Q hat. And we know N being the size of the sample. Substitute the values in. There are. So pause and decide what conclusion you can make from that. Okay, so this says that we are 95% confident that between 33.2 and 46.8% of the population drink fresh fruit juice. When I say we are 95% confidence, that means the probability that people in the population, in the full population, drink 100% pure fresh fruit juice is between 33.2 and 46.8%.